So if I am interested in computing this expectation now, so imagine I have a lot of instants. So the I some instant here and j some instant here. I minus 1 is going to be here, and j minus 1 is going to be here. I'm interested in computing this expectation of hi, hj, mi minus 1 and mj minus 1. Now, using the property of the conditional expectation, so we did it from just quickly reviewing it. So that if you compute the expectation of the conditional expectation with respect to the sigma field, it's equal to the expectation. So if I treat this as so I can write this as the expectation of the same quantity given, j minus 1, j minus 1. Okay. This entire quantity is going to come here. This entire quantity is going to come here. Now in fj minus 1, I can see obviously that hi, since it's predictable, is fi minus 1 measurable, and fi minus 1, the filtration at the time I minus 1 is contained in the filtration at time j, so this is fj measurable. This is also fj measurable, hj. Mi minus 1, okay, by the similar argument you can say it's hj measurable. The only thing that is going to be interesting is this quantity. So if all of this is known in fj minus 1, so I can pull them out of its expectation. So I can have expectation of hi, hj, mi, and mi minus 1. Okay. And what remains inside is mj minus 1 given fj. So fj minus 1 is the set of all information up to the time j minus 1. Okay? While mj is the value of the process at time j, and mj minus 1 is the value of the process at mj minus 1. So when you take the increment, you are talking about something that is beyond fj minus 1. So you can say that this guy is independent of fj minus 1. That is independent of fj minus 1, so we know that if a random variable is independent of a sigma field, and you compute its expectation, is going to be equal to the expectation. Otherwise, you can get rid of
sigma field.
If you wish, you can get rid of this. Actually, I can say that
martingales.
So now m and n process is since a martingale, so the expectation of mj and mj minus 1 should be same. So this must be 0, and hence this entire expression goes to 0. And what this shows that this entire expression goes to 0. I'll move back here. So this means that in order to compute the expectation of x in the square, I need to compute the expectation of this guy. Let's compute the expectation. And obviously show that this expectation is equal to this expectation. So how can we do it? So if I have an expectation of hj times mj minus 1 square, should I get rid of this and write it also with the some space?
n स्क्वायर सब मार्टिंगल है, इसके लिए जो एग्जिस्टेंशियल मार्टिंगल होगा वो m
इसलिए
जो m स्क्वायर है वो सब मार्टिंगल
इसे सब मार्टिंगल,
तो इसके लिए एक तो एग्जिस्ट करती है कंपनसेटर मार्टिंगल एग्जिस्ट करता है, तो जो
we will
मार्टिंगल
see that probably we will don't need that actually this expectation. So we can do it So here's the thing, expectation of mj or hj times mj minus 1 square, okay, is equal to this. I can do same, so just like if the same trick that I did there, j square, so this is same as the expectation of j square mj minus 1 square, okay, given fj minus, right? The same trick. Okay? Same issue. So hj square is fj minus 1 measure, so I can take it out. I have hj square. So what remains inside is this mj minus mj minus 1 square fj minus 1. But I know this guy is 1. So if we use the previous proposition, actually, the difference of this square and the square of this one side. Actually, the square is going to be same as 1. mj square minus mj minus 1 square. Okay. Mj square minus expectation of mj square minus mj minus 1 square. Okay, I can write in this manner as well. Okay. Given
fj minus 1.
Okay. Now, if a n is a compensator for mn square, the question is, can we follow as an is compensator, okay, for process mn square? The question is, can we follow this thing? What would be mj square?
M naught
It's going to be m naught square
plus
some martingale. Okay, I know what martingale. M prime j
aj
plus aj.
and j square
mj
Minus
square
one,
minus mj
minus
minus 1 square is going to be what?
naught is there.
Not square, so this will go away. Right? So you're going to have the mj prime minus mj minus 1 prime plus aj minus
aj minus 1.
aj minus 1, right?
Expectation plan.
And if I apply the expectation, okay, the next system, if I apply the expectation of, okay, if I apply the expectation of mj minus 1 and
mj and mj minus 1.
square is going to be equal to expectation of mj prime minus mj minus 1 prime plus, or given, I must say, fj minus 1, right? So given fj minus 1 plus
Expectation of aj
expectation of aj minus aj minus 1 given
fj minus 1.
fj, right? So you have three expressions.
Martingale rule.
Now this is for sure zero, because this is independent of fj minus 1. So,
Yeah, like
so it's going to be equal to the expectation of mj and mj minus 1. Right? Okay, but since it's a martingale, so expectation of mj minus 1 have. So it makes sense to say that, you know, not really equal to square,
expectation.
but the expectation is equal to square. Okay? So this is going to be, with those calculations, going to be expectation of Hj square times expectation of
AJ
Aj minus Aj minus 1
given
given
Fj minus
Fj minus 1.
for it.
And I can go backward in this manner. So I can say that, you know,
Size.
so this is Hj square is Fj minus 1 measurable. So I can insert it inside. And then the expectation of the conditional expectation is going to be expectation. So the key thing is that Fj minus 1 is so Hj, since it's predictable, is Fj minus 1 measurable. So you can insert it into the expectation. Then the expectation, so you're going to have the expectation of the conditional expectation. So which is expectation? So we get what you. Nice. So next part is about we're talking about something called the stopping times. Okay. So stopping times is essentially a random variable. Okay. And since it's a time, okay, so it can have many kind of significance. For example, you are trading. Okay. You are trading a stock. You have a portfolio. Okay. And you say that okay, I'm gonna sell the stock, the current stock that I have, the units of the stock, at a time when it becomes, say, for example, 1/2 of the original price. So in other words, so imagine you bought some stock at time S0. Okay. You expect it to go up. You will not make money out of it. But it can go down as well. So I'm going to say, I will immediately sell this stock at a time tau. Okay. When this, at this time, the stock becomes, say, for example, half of what you paid. Okay. So this time is a random time. So you don't know that when, you don't know that when this is going to happen. At what instant after the time 0 in the future, the stock is going to be the half of what you paid actually. Okay. So if it becomes half of what you paid for the stock, you will immediately sell it because you don't want to lose more. Okay, you expect it to go up, but unfortunately if it is going down, so you have a tolerance level at it. That you can't tolerate more than losing more than half on this stock. The moment it crosses half or becomes lower than half, you just sell the stock. Okay. Now this movement, okay, which I have no idea when it's going to come, okay, is the stopping time for me because at this time I roughly stopped trading this stock actually. I just showed the things. Okay. So that's just one illustration. Stopping times are more general than that. So I like to do what I like to do. Define stopping time, maybe some examples, and maybe some basic algebra of the stopping times. Stopping times are going to play a very crucial role afterwards. Because sometimes what we like to do, we will like to stop our process. In other words, so imagine you are a gambler. Okay? So if you think from a gambler's perspective, if you won enough, or if you lost enough, you want to stop. If you won enough, okay, you're going to say, today is my good day. Okay, I have won a lot. So let's not be greedy more greedy, and stop the game and go home. Okay. So if you stop the game, that means that kind of you have to stop your gain process that you are making, okay, whether it's losses or winnings, okay, you have to stop at a random time. So we will also need to deal with what we call the stopped stochastic processes. So I have a stochastic process. The GAN process is the stochastic process. But what if I want to stop this stochastic process at a certain time actually? Okay. We'll be interested in that. Stop the stochastic process. Okay. You can ask a lot of interesting questions. If the stochastic process is a martingale, is the stochastic process is also a martingale. If you're playing a game and the game is fair, and if you are playing this a game in which the payoff are being, for example, determined by a stopped stochastic process. So is it going to be still fair? Is it going to be still a martingale? So you can ask many interesting kind of questions to this famous time structure. So first, we would like to do things with mathematical, some examples and some properties of the stopping time. In the next discussion, we will start using these stopping times. Okay, so what's a stopping time? Many ways to define it. Let me put a formal definition. Any equivalent versions of it. So, stopping time is a random variable. Thanks. So, it's a random variable. It's denoted by tau. Okay. So if it's a random variable, it's going to be a measurable map from omega into R, obviously. And I want to pose to infinity because it can also happen that you never stop. For example, the stock never goes down before below your choice of the level actually. Okay, so in that case, we'll say that the stopping time is stop. Not before that.
हम टाइम के लिए वेट तो कर सकते हैं ना जिससे वो स्टॉक की प्राइस बढ़ जाए.
One of the we are interested in that it shouldn't go beyond a level or lower level. But when this is going to happen, we don't know. So why I'm including infinity here? Because maybe it never happens. So in that case, the value of the stopping time is going to be infinity. That's you're not going to stop it. So a random variable stopping time relative to filtration. Always have a filtration to filtration Fn. Okay. If this happens. Any n bigger than or equal to 0. Whenever I am saying that n is bigger than or equal to 0, I mean discrete n's. Obviously, n is one is smaller. The event actually that omegas and the trajectories, sample points for which the tau of omega achieves the value is a measurable set in itself. Because your stopping time is going to be the nth moment, this information should be present in the in the market that they are in the fluctuation. So it can stop at any time. So it can stop at 1, 2, 3, and so on and so forth. So if it is stopping at an instant n, process of the random variable that is stopping at the time n, this information must be presented in what we call this fluctuation. Okay? We'll do a practical example. You will see it's not an unusual thing to imagine. So what we are saying, the sample paths for which are the trajectories, the random trajectories, are the paths for which omegas for which the stopping time takes the value n should always be a measurable sample should be able to measure its probability. Because if you are here, it means that you can compute its probability. Imagine it's not an FN, it means that you can't compute its probability. We are talking about something which is beyond probability measures. You should always be able to compute the chances of such kind of a
Means really can do stopping.
lots and lots of okay. For others, you can have many different
Of course, for वो जितने भी मेरे rules है something.
ठीक है जी? By the way, this thing, a quick remark, is also equivalent to saying that for omegas for which the stopping time is less than or equal to, in other words, stopping time can be any time up to the n. This is also measurable. In other words, if this is true, so from this I can deduce this, and from this I can deduce this. So how can I, for example, deduce this from this item? So what you can do, when I'm saying that omega such that, let me just write tau is n, okay, tau is n, or tau is less than or equal to n. It's same as that maybe you stopped at tau 0, or you can stop at 1, or you can stop at tau is equal to n. Okay. Now this guy is measurable where?
0.
At 0, by definition. So if it is measurable in f naught, so it's also measurable in f(n). So if this guy is measurable in f1, so it's also measurable in f(n). So that's a measurable segment. And obviously, if you have this, you have this answer. What would be some examples? Typical example is the first hitting time. In other words, imagine you set a barrier for something. For example, I set a barrier that, okay, if my stock goes below 1/2 of what I paid, I will stop. It could be a barrier from below and it could be a barrier from above as well. So, as the process is going, here's the thing to do here. So imagine so you set up this barrier. In other words, I have this process which is going randomly. The moment it hits, it can go crazy, it can go in any manner actually. So the moment it hits what do you call your
Barrier.
required level or barrier, you will stop it. You will stop doing whatever you are doing. Or you will, for example, sell that stock. Okay, the cell can keep on going up and down, but you just got rid of it. Okay. So how can I precisely define it? So imagine. So this is